Now we're going to talk about James, the Webb Space Telescope achieving the amazing. Can you have 5 minutes? Okay, have 5 minutes.
Let's take a break for 5 minutes while we work technical.
You work technical. You want me to talk to them?
No.
Don't want me to talk to them. I won't talk to you. I'll just mumble to myself a little bit. Let them talk about it. One of the things that we found is I got a new iPhone 2 months ago or so. And I did this facial recognition thing on it so they could recognize me and come on without me having to put in the super secret code. And so I didn't realize that it wouldn't recognize me with a face mask on. And I forgot my super secret code. So I was sitting in the airport this morning, just trying over and over and over again to get the iPhone to activate with this code I forgot. So I finally just took off my mask, pretended I was having a drink of water, had it do the facial recognition, and haven't turned it off since. Technical challenges are usual for us. I used to do theater. I did some theater writing, theater production. Opening night sometimes are just amazingly difficult. So we got Mark's thing here. And we got Mark's thing there. All right. And I do see that while we were waiting, I have a little screen here, like a little iPad thing. That used to have a button on it, big red button that said turn off AV system. And they turned off my iPad so that I can't do that to you. So how are we doing?
I guess we'll give it a shot.
We'll give it a shot. Be patient and tolerant. All right. First session. Achieving the amazing. I want to thank Aerospace Corporation for sponsoring our session here. Thank you very much, Aerospace Corporation. And our moderator is Mark Clampin. He's Director of Sciences and Exploration Directorate at NASA. Welcome, Mark. Come and get your panel.
Okay, so we should have the rest of our panel come and take a chair. Let's see if we can go back to, back to the first slide.
Mark, just tell them to advance. Just say next slide. And
Okay.
they'll advance it from up there.
Okay. Yeah. Take the mask. Okay, Erin?
She's coming inside.
She's coming. Okay.
Or you can control it, Mark. That's it.
Sorry?
You can control the slide.
Okay. Okay, so good afternoon. This is the Webb Telescope Achieving the Amazing, the first session of the meeting. So I'm Mark Clampin. I'm the Director of Science and Exploration here at the Goddard Space Flight Center, and I'll be moderating this panel. So right now, there's a real palpable sense of excitement as we go through the commissioning of the James Webb Space Telescope. And you should be able to spot the people in this room who work on Webb because they're all grinning like Cheshire cats right now. And the ones that aren't are just plain giddy. So it's obviously going very well, and we could, spend the whole hour just staring at this fantastic image here. But instead, what we're going to do is have our panelists start by talking about where we are and what's happened over the last 3 months after the launch. And then during the Q&A, people can ask questions and we'll get a sense of where we're going to go next. So our panel this afternoon consists of Charlie Atkinson, who is the JWST Chief Engineer at Northrop Grumman, Lee Feinberg, who is the JWST Optical Telescope Element Manager at the NASA Goddard Space Flight Center. Erin is the JWST Program Manager at Ball Aerospace. And Macarena Garcia Marin is the JWSTMIRI Instrument Scientist for the European Space Agency. So without further ado, I'm going to let Charlie Atkinson start, and he'll tell you about the deployments and the first stages of operating James Webb. Thank you.
Up, down, but we don't know which way is up, which way is down.
I'm not sure that quick.
There you go.
There we go. Cool. Okay.
Which way is up?
So I had to do that. So yeah, figured it made sense to start off this discussion with the first things that we did with JWST once it was launched, and that was to go through the deployments. We spent the first 2 weeks, 14 days, executing the deployments and trying to get that compressed into a very short time span to describe to you what was happening. I figured I'd just go through the deployment video, which compressed 14 days down to about 1.5 minutes. So first we started with the solar array, which happened right after launch, right after separation. And we just paused. Awesome. And we are dead. All right, how do I phone a friend? At least most people got that. Any clue how we get this going again? Okay, cool. All right, we'll try again. So first the solar array deployed shortly after separation from the launch vehicle. Awesome, still going. Then on day 2 was the antenna deployment to give us comm. And then we deployed the sun shield pallets. This is what holds the membranes on the sun shield. That was on day 3. Then on day 4, we deployed the telescope tower, which gives us an extra 4 feet of separation from the telescope to the warm observatory, warm spacecraft. Then the trim tab came out, and then we started the deployment of the membranes themselves. First by unfolding the covers and then extending out the booms on the side. These are the mid booms that hold the 5 layers of membranes from its folded configuration out to its fully extended location. You can see underneath is what we call the DERSA radiator shed assembly, which is an additional shading that provides some thermal control for the observatory. Then we went through a multi-day process of tensioning the membranes. Then we deployed the telescope with the secondary mirror coming out and going into its final position. And then the aft deployable radiator deployed, which gives us additional cooling to the instruments. Then we deployed the primary mirror, first one wing and then the other. So that was the full 14 days compressed down into 1.5 minutes of what the deployment sequences entailed. Let me reel back now to when we started. So just after launch, 30 minutes after launch, just moments after we separated from the launch vehicle, is when the solar array deployed. That was done automatically. We weren't sending commands. We wanted to make sure it happened in case we had some kind of comm issues. We had that already pre-prescribed to occur at a certain time after we separated from the launch vehicle. And we had telemetry that was telling us, yes, we fired the release devices. Yes, we got the thing extended with micro switches tripping when we got to the full extent. But what was really awesome was the camera that was on the upper stage actually got us an image of what was happening. And me sitting at home watching this, I was like, oh my gosh, that's awesome. So not only did we have telemetry telling us that, yeah, we had deployed, but we actually also got a visual confirmation, which was really cool. But this was the only visual confirmation that we had because we don't have cameras on the observatory watching the deployments as it does deploy. But we did have this tool. Come on, come on. Do we have another way of doing this? Keep going. Thank you. So we did have a tool called the Observatory Visualization Tool. And what it did is it took the actual telemetry that was coming down from the observatory and fed it into a model and updated the configuration of the model based upon the telemetry we were receiving. So on day 2, when we did the antenna deployment, the resolver data that was coming down in the telemetry stream was fed into this model and it was updated real time. So we could actually see with this tool what was actually happening on the observatory, which really helped us get a good feel for the configuration of the observatory throughout the deployment process. It was an excellent tool to use. Yes, we had the normal telemetry stream that with the resolver actual numerical data, but having that tool was really fantastic. Same thing with day 3 when we did the pallet deployments for the sun shield. that resolver data and the motor telemetry was fed right into the observatory visualization tool, and we could see what was actually happening. So it was a really cool tool that was implemented. And then all the way up to day 14, when we completed the deployments with that last wing that was deployed, Paul Reynolds got on the loops and announced that the deployments for JWST had completed. 14 days of a lot of nail biting and tension, but it was all done successfully. We were able to then congratulate the team and move on to the next phase. So in total, we had 178 release devices. These are the things that held the observatory into its launch configuration and made sure that we could survive the rigorous, violent launch environment. 50 deployment structures that deployed with 100% success. So with that, I'll turn it back over. And the down arrow.
Down arrow, okay. So let's see. Erin and I decided to divide and conquer a little bit, and she's going to talk more about the algorithms that we've been using to align the telescope, but I'm going to tell a little bit of a technology story of the mirrors, and I'm going to start all the way back at the beginning and then fast forward up to commissioning, so you can kind of get a sense as data has been coming in of what has been going through our minds as we see results. So let's see, down arrow, you said? Yeah. Okay, so this is like going all the way back to the beginning of the program. We used to have this chart that we would use to explain to people, this was one of the key technologies we needed to develop Webb. And it's really true of any big telescope. It's always about like the primary mirror. The mirror is going to be huge. And in the case of Webb, the primary mirror had to be super lightweight. And we had a metric, which we call aerial density. We were trying to reduce that aerial density relative to any mirror we had ever flown, 10 times lower aerial density than say what was used on Hubble, and a couple times less than what was used on Certif or Spitzer, as well as the polishing time had to be done faster. And so this was kind of like the grand challenge that we had and a chart that we used. And from that came a technology program. It was actually a collaboration between NASA, it was actually Air Force Research Labs of DoD and NRO, and we each invested money and to develop lightweight segmented mirrors. And we were shooting for the 15 kilograms per meter squared I showed in the previous slide. And we developed, and we started with 8 different mirror architectures, but we actually built 3 different mirrors, and they were very different mirrors. One of them actually, the one in the lower right here, the Goodrich mirror, which is in Danbury, Connecticut, it was literally, we call it a bed of nails. It's a large number of actuators with very high authority. There was a mirror which was built by Kodak in Rochester, New York, which is now L3 Harris, which was an ultra low expansion glass mirror that had actuators for correcting gravity distortions, but you could take those actuators out. And then we had a beryllium mirror that was a semi-rigid mirror, and the only actuator you would need is the one at the center to change the radius of curvature. And so we developed these 3 mirrors, and when the prime contractor was selected, which was TRW, and Charlie was part of that team, when we first met, one of the first things they said to me was, well, our team only has the beryllium mirror and the ULE mirror, and we're going to, and the proposal was to do a down select between those 2. And so what we did is we actually took those 2 mirrors to the cryogenic chamber in Huntsville at Marshall, and we tested them. And what we found was that the glass mirror had what we call astigmatism. You can kind of see it there, the red shape. And the beryllium mirror was very uniform. And it just turns out that beryllium has just very ideal properties at these very cold temperatures. The glass mirror has great properties at room temperature, but when you cool it down, it tends to distort a little bit, but more importantly, it's temperature sensitive. And that was an issue for us because first of all, if you look, and this is actual data from earlier this week of the primary mirror, and you can see the different temperatures, these are in Kelvin, from the top to the bottom of the primary mirror can be as much as 20 Kelvin. And so if we picked a mirror that was temperature sensitive, every mirror would have had to hit that exact temperature, and it would have had to been what we call cryopolished at that temperature. And it would have been a much more difficult challenge. And so for that reason, beryllium was selected, but we knew that it was going to be a challenging fabrication. And so we fast forwarded to the development of all these mirrors. We literally had to facilitize 2 different places. One was a machining facility in Alabama, and one was a polishing facility in Richmond, California. We developed an engineering design unit that we use to take it to what we call technology readiness level 6, where we do environmental testing to show that the technology is ready to fly in space. And then we actually had to make the mirrors. We had to test them at cryogenic temperatures. These mirrors were so lightweight, they distort under gravity. So we never actually got a mirror that was exactly like the way it would be in space. We were able to test the mirrors. Now I'm going to fast forward into 2017. We put the whole telescope in a large cryogenic chamber in Houston. This is the chamber A in JSC. And for the first time, we could look at the entire primary mirror, all 18 mirrors. We were adjusting their curvatures to match each other, yet we still were under the presence of gravity. And so you can see these, what we call fringes across the primary mirror. They have these shapes in part because of gravity. And so we were never able to remove the effects of gravity. And we had to demonstrate through modeling that all these mirrors could match each other and would work properly at zero gravity. And by the way, when we got this first measurement, it just so happened that a hurricane had just landed about the evening before and decided to last for about 5 days. And yet the fringes look like this, and we were still pretty happy despite the hurricane. And now fast forward to commissioning. Some of you who may have followed may have heard, initially we were very excited to find these 18 spots representing the 18 mirrors. Well, the very next thing we did is we moved the secondary mirror. We did what's called a focus sweep, and we got data at different image planes. And we were able to put that in special models that we have that can recover what is the shape of the mirror that would give you that. And we were very happy to learn there was no effects of gravity, that we had gotten the gravity right. That was the first time we saw that. And that was our first hint that, yeah, this looks like we made the mirrors right. But then we went through the alignment process, and in doing, we separated the 18 segments, and we were able to kind of align each of the 18 to the secondary mirror. And by doing that, we eventually kind of convinced ourselves that each mirror had to have been pretty much correct. And we built a lot of confidence that we had made the right mirrors at that point. And we've actually since then been able to do that model retrieval that I mentioned. And we've actually compared it against the data we took all the way back in 2010. And we're finding it's amazingly close. We call this the figure residual of the primary mirror, but it's amazingly close to what our zero-G prediction was coming out of Huntsville 12 years ago to a few nanometers. And since then, what we've been doing is we've been doing more frequent measurements of that primary mirror. And the way we do that is inside of the NearCam instrument, we have these little lenses we can put in with different amounts of power. Each one of these images is an image from one of those different lenses. And the flashing you're seeing back and forth is the model versus the data. That's how good we call that phase retrieval. And we're recovering down to like the nanometer level, the surface shape, and the surface shape is so good that astronomers are going to be really, really happy. I'll just leave it at that. And so where does that get us? That gets us to this image of a star, which some of you have probably seen by now. But the most important thing to know about this is from the optical point of view, the star is actually way smaller than this bright spot. It's only a couple pixels wide. It's just that there's so much light that you're seeing the effects of diffraction. But more importantly, there are other stars in this image. We call those over the field. And they're also all really small, which means that we call it the field dependence is right. And this was a pretty long exposure in the sense that it was 2100 seconds. It was done by a mosaic. And so the pointing system, the guiding system, which keeps us stable, the ability to take data and send it to the ground, the ability of the system to calibrate the data, all of these different pieces are working remarkably well. And this is the reason we're so giddy.
All right. So as Lee mentioned, we're kind of splitting this. So I'm going to talk more about how commissioning is going and how we got to this beautiful image. There we go. So first, how do you even start tackling the problem of commissioning a $10 billion first ever segmented space telescope? And the short answer is practice, practice, practice. We built a 1/6 scale model of the telescope at Ball. We had flight actuators on the back of each of these smaller hexagons. And we had to practice through the whole commissioning process, developing the algorithms to do the phase retrieval and do the alignment process and prove it out on this test bed. We also had a lot of rehearsals here at the Institute up at Baltimore, just to work together with the team and the other systems that we are so dependent on, like the guiding and the thermal stability that affect our measurements and our alignment abilities. And finally, we had an integrated telescope model. And Lee touched on that a little bit, that we couldn't test everything on the ground because of gravity and other things that we just can't take out on Earth. So in order to prove to ourselves that we had the right process, we used our integrated telescope model to run through end to end from deployment images through our fine phased and even our multi-field alignment process, where our team would perturb the mirrors in the model, send it some commands, and the model would retrieve what the images would look like and where you've moved things and how you've disturbed the wavefront of the primary mirror. And so that was a great tool to get the team up to speed and to prove out our process. And we discovered a lot of really good check marks along the way, intermediate decision points and intermediate criteria that have turned out to make our job a lot easier. And having those along the way and refined intermediate criteria have made this final step that we're in now just a breeze. So telescope alignment captured in 7 short, easy steps. We start out with our segment image identification. So we do an image mosaic on the sky, and we eventually get down to figuring out which blob is which mirror segment. And so we can, and I'll go through each of these phases in a little more detail on subsequent slides. Then we take all 18 spots and we align each of those 18 spots individually to our best ability. And that's taking out the segment wavefront error and aligning each individual segment. So once we have that done, we kind of have 18 independent telescopes going on. So now we need to stack them and make one telescope. And that's our image stacking process. And that gets us ready then to do our iterative coarse and fine phasing that we use some specialized alignment hardware in NearCam on orbit to do. And then finally, once we've aligned to NearCam, which is that beautiful image that was released last week, then we have to check all the rest of the instruments. At that point, we're aligned to NearCam. That's our wavefront sensing alignment instrument. But we have all these other instruments across the field of view. So we're in that process now of taking a look at the other instruments across the field and seeing if we need to make a global correction to kind of balance the wavefront across the instruments. So our very first task is to just figure out where we are and where the segments are. So we do a large scan, and we planned to do a very large scan about the size of a full moon on the sky. And that's because at the end of the day, our pointing system, our ACS, is down on the spacecraft side. And our telescope, our segments are through all of those other subsystems and deployables like the DTA, the secondary mirror strut, the segments themselves. We had to move from their launch snubbers 12.5 millimeters out in piston. So all of those uncertainties stack up. And so we spent a lot of time on contingency methods for what if we don't find all 18 spots right away? What if we do this big scan and we still don't have all the spots? Maybe a couple segments are off pointed a little further. So we spent a lot of time on that. But as with the rest of commissioning, Webb has performed as expected. And so we took our raster scan and all 18 spots were there. So we perturb each segment one at a time from the ground and take an image before and after that perturbation so that we can identify each segment. And so this is that same picture of the image mosaic, but with the segments identified. And you can see the 2 wing segments are there and grouped nicely together. And most of the center segments were grouped in between as well, with a couple outliers. So we go through then the process of the segment alignment. And this is where we're trying to just align each individual segment as its own telescope. And we do that through secondary mirror focus and do phase retrieval on each individual segment. So you can see the before and after. And is really, it's obvious that we made some big corrections, big relatively. They were still well within our expectations and well within our actuator range. And then once we have 18 beautiful telescopes, we need to get it down to 1. So we do this image stacking process, and it's iterative. So you can see the progress of the energy that are hitting those pixels in the top and bottom image after a couple iterations of image stacking. And so we're getting there. We're getting to a nice aligned state, a nice single spot at this point. And this is where we were able to then turn it over to NearCam instrument to start doing some of their checkouts, because we had this nice aligned spot. And that's because our next step relied on some very specialized hardware in NearCam, and that's the DHS, the dispersed Hartmann sensor. It's like a prism in NearCam. It's in the filter wheel, and it splits the light into these barber pole patterns that we can then measure the angle of. And that tells us the vertical displacement of one segment to its pair, its neighbor, and what that piston difference is, so that we can then align all of the primary mirror segments to act as one monolithic mirror. And this is where we initially had some concerns when we get to image stacking. And then we had to wait a few days while NearCam did their checkout, and we had to check out the filter wheels. And at this point, we're still cooling, right? We are doing all of this alignment as we are cooling down, and that does affect the wavefront. Even though the mirrors themselves are thermally stable and have great properties at cryo, the whole rest of the system has to cool down and move a little bit. So we were a little concerned that we'd have to maybe restack at this point. But the thermal stability and just the cooling of the telescope has been as expected or better. And so we didn't run into problems here, which was great news. And so we do this course phasing to start aligning to one monolithic primary mirror. And then we iterate that with our fine phasing process. Oh, we lost a slide. That's okay. And the fine phasing process, Lee showed those great images of the weak lens hardware. And that's, again, some specialized hardware in the NearCam filter wheels that allows us to take the defocused images without actually perturbing our telescope state. Once we got to that beautiful fine phased image with the diffraction spikes, we don't want to move the secondary mirror at that point, right? And mess it up in any way. Because if we do, we'd have to iterate back to get it aligned, and that takes time. So we have these weak lens hardware that really allow us to get even more aligned and fine phased as a monolithic primary mirror without disturbing the alignment of the telescope. And so now we're in the multi-field process and looking at across the field, and things continue to go very well. So yeah.
It works. Hi, everyone. My name is Macarena Garcia Marin, and today I'm going to talk with you about the science promise of the Webb telescope, where we have, I think, the whole astronomical community and the whole community in general, it's really excited about. So you've seen the primary mirror and all the work that's being ongoing, and things are going very well. Behind the primary mirror, we do have the science instruments, and Webb has 4 science instruments and 1 guider. So the science instruments have many different capabilities, but in summary, you have cameras and a collection of filters to do images in the near and mid-infrared, several flavors of spectroscopy that allows us to disperse the light of astronomical objects and really understand their chemistry, velocities, and their compositions. And finally, coronagraphs that are, as you know, I'm sure, they do actually block the light of bright targets like a very bright star or the nucleus of a galaxy. And that allows the observer to actually see what's around, like planets or a structure of the galaxy. So at the center of ISIM, you do have NearCam and NIRIS. NearCam is the very powerful and sensitive camera that has been used to do the wavefront work in the primary mirror. And it also has spectrography and coronagraphy. And NIRIS is also a very sensitive infrared camera. Next to NIRIS, you have FGS, which is the guiding system Lee mentioned before that really keeps the telescope stable. On the outside of ISIM, you have the third near-infrared instrument. It's called NIRSPEC, and it's really a powerful it's a spectrograph, but it has 3 different flavors of spectroscopy. And one of them is a really interesting array with a 250,000 little windows that can be configured to observe up to 100 objects at the same time. And finally, we have MIRI to your right. And MIRI is the only mid-infrared instrument on board. So essentially with Webb, we cover from about 0.8 to 5 microns in the near infrared, and with MIRI from 5 microns to 28 microns. So it's a really very broad wavelength range. So what are the gains in resolution and sensitivity? So you see in this animation the image from Webb that you just seen before, and superimposed there is a simulation of how Spitzer would have seen this at about 3.5 microns. And actually the credit of the image is not there. It's a pity, but you see how the combination of the large size of the mirror, which is about 5 times greater than Hubble and about 45 times greater than Spitzer's. So the combination of that really large collecting surface of the mirror and a sort of very sensitive and cool down instruments, because all of the instruments operate at really low temperatures. So the combination of those 2 aspects really gives great detail and great sensitivity. So in summary, Webb will observe smaller, dimmer, and really more distant objects. And that's for distant objects, but in the local universe, it will observe galaxies, planets, everything in really great detail and with great sensitivity. So for instance, with the Spitzer, there were many details in the faint areas around galaxies we wouldn't see. With Webb, we are gonna see them. So Webb is an observatory. So you can essentially observe everything. It doesn't have a specific science topic, but it has science areas that aims at covering a really fundamental science questions that were defined at the beginning of the mission. And the first one is, what did the early universe look like, and when and how the first stars and galaxies were formed? So that's one of the fundamental questions. The next one is understanding how galaxies and black holes actually form. There are many still open questions about how black holes form at the center of galaxies and how they evolve from the very beginning of the first galaxies up until now. So Webb will provide a lot of interesting data to actually answer those questions. We also look into the life cycle of stars from their birth, the whole cycle until their death. And of course, there will be investigations of planetary systems. That includes our own solar system. So from Mars beyond, we are going to be able to actually see and investigate the solar system planets. And finally, one topic that I think is really going to make a difference and is really captivating the imagination of everyone is the studying of exoplanets and really studying their atmospheres in search of signatures, of chemical signatures of components that may indicate the presence of life. So studying exoplanets is going to be, I think, a great field of interesting discoveries for Webb. So in the next slides, I'm going to very briefly talk about a few of these topics, and then we can go to the Q&A and really continue. So this, I'm sure many of you have seen it. This is an image from the Hubble Space Telescope. It's a Hubble Ultra Deep Field. This was obtained by pointing the Hubble to a region of the sky where on the naked eye, you don't see anything, it's just dark. And it's really small. It's like you take a straw, the projection of a straw in the sky. And if you point the telescope for many hours and days, this is what you obtain using different filters. So there are thousands of galaxies. The oldest galaxies we've seen so far, they are captured in this image. So how can Webb build on this? Well, we know these are not the first galaxies that were formed in the universe. So if you go back about 3.5 billion years, even maybe more, the first galaxies did emit light in the optical. So as that light travels to us in an expanding universe, the light sort of stretches the wave. And so it moves from the optical to the infrared. That's where Webb will make a difference because it's just an infrared telescope. It's going to be able to detect those very first galaxies and stars that were formed and really give us an idea of, you know, the very beginning of the universe as we know now. And this is just a depiction of that. So after the Big Bang, everything was really dense and hot, so no photons were out. Then the universe became neutral, which is called the Dark Ages, and nothing, we didn't have signal. And then many years later, the universe started to reionize. The hydrogen started to reionize, and really slowly stars and galaxies started to form. And so that's the period we are actually targeting with Webb. Of course, it will not only see that, it will see all the galaxies from that very primeval ones until the ones locally. And that will give us really information of how they form initially and how they evolve until the point we see them now. So really a lot of information and exciting areas of discovery. This is a video. I'm not sure I'm on. Yes. So that's again another image from Hubble. It's the Pillars of Creation, a very famous nebula. And what you see there is a lot of dust. Behind that dust, as you see now, there are stars. Really, it's a nursery of stars. The stars are forming really very young and evolving in there. But with the optical, you don't see it because it's just you have all this dust. The amazing thing about the infrared is that it heats up with the light that emits from the stars behind. And so it makes it transparent. So with Webb, all those features of dust you can see in that image, they will be essentially invisible. We're going to be able to peer through that dust, not only to observe newly stars being formed, but also to observe planetary systems information, what is hidden behind all the dust, for instance, in galaxies that are in a certain position. So it's really going to be like lifting the curtain of dust in the universe and seeing what's behind with very, a lot of sensitivity and great detail. And finally, studies of exoplanets. For exoplanets, mainly, thank you. One thing that will be essential for exoplanets studies is going to be study their atmospheres with the transit method. And the transit method, essentially, you observe a planet as it transits in front of the star. But for smaller planets, you see a small dip in the light emitted by the star. For larger planets, a dip is bigger because it just blocks a larger region of the star. And the amazing thing is that as the planet goes in front of the star, the light of the star filters through the planet atmosphere. And when we measure it, it actually has all the chemical signatures of the atmosphere of the planet. And then you can start, inferring what's in there. Is there water? Is there oxygen, methane, et cetera, et cetera. And then you can start thinking about the conditions of that planet and whether or not there will be life-friendly, if you will. This is my last slide, and I think it's a good point to actually start the discussion. Thank you.
So, Q&A time. We have students over here who are going to run microphones around. Come on, students, as my father would have said, students. Grab yourself one. So who has the first question? Anybody? Anybody up there? Run the microphone up to him.
Hi, I just very impressed with about the deployment stage, the number of actuators and release mechanisms you had. I'm just kind of curious whether, when initially being faced with that, what I'm sure must have been a sort of a daunting task of having all those go right. I'm just curious if you took any special approaches as far as managing risk or any special attention that you paid to that problem.
There should be a couple of microphones still up here.
There we go. Okay. So yeah, with the deployments, this is definitely the most complex deployment that we've ever undertaken. And really what gave us confidence that it was going to go successfully is the degree of testing that we did on the ground long before we got to the point where we launched. So we tested it, the individual component level, we tested at the mechanism level, and we tested at the observatory level to show that all of those deployments were going to go successfully. We also did a lot of work with the provider of the non-explosive actuator device. That's the release device that we used. We worked, both Northrop Grumman and NASA worked shoulder to shoulder with them to improve their process, to make sure that all the right inspections were done during the whole process. Anything that could potentially lead to a hang up in a release. We had special inspection steps that were checked by numerous people. So I think it was just a rigor that we applied in the testing program that really enabled us to have confidence in the score. Next question.
I have one from online.
We have a question from our online attendees, and forgive me if this has already been addressed, and I'll add my own part. What is the expected operational life of the James Webb Space Telescope? And based on other missions that we've seen out there lately, is that a conservative number? And you're truly expecting more?
Well, let's see, this has come up. People have asked this question. I think our system engineer, Mike Menzel, answered this question at one of the press conferences when he said, one of the main life-limiting items is fuel. And he said at that time, this was earlier in commissioning, that it was approximately 20 years was the number he gave, but that we'll be updating that number as we better understand, our trajectory and our orbital dynamics. So that's the main thing that we understand to be life limiting. It turns out that the system actually wasn't required to last that long, but really come down to things like electronics and mechanisms. But we do have a lot of redundancy. Almost all electronics are redundant on the system. And so far we haven't really had to switch over, electronics boxes, for example. So as best we understand, it's going to be fuel limited, but it's hard to predict.
Over here.
Hi, congratulations on the success of the deployments and the instrument calibrations so far. My question is, how stable do we expect all of the mirror positioning and instrument calibrations to be, and how frequently would they have to be updated?
So it's part of the baseline plan to measure the wavefront of the telescope every 2 days. And we expect to apply a correction based on that data about every 2 weeks to account for thermal drift and things like that. But all of that is done within the fine range of our actuators. And so we don't have to go through an iterative alignment process if we stay within the fine range of our actuators. So we'll continue doing that every 2-day cadence for data collecting for the life of the mission.
Right here to in the center. In the center.
So congratulations again on all the success so far. My question was really about the simulation that you showed that was taken around 2010, and that the real life data now almost exactly correlates with it. With the system that's so complicated and so many bodies and companies involved, how do you make sure that everything still works when you have so many different subsystems integrating together for so many years?
Well, first of all, that is an absolutely excellent question, because that was one of the big challenges. Is there was several different companies all working together. I think one of the key things is you need really good system engineering. And one of the things system engineering does is it doesn't just say, what are my specifications and did I, actually test them, but it documents things. And I have to admit, I didn't appreciate this going in, because I was used to doing these Hubble servicing missions, which took a few years. And a lot of times we did the documentation after we got the hardware in space, because they were 3-year efforts or 4-year efforts. But on a 20-year effort, the documentation is actually really important as well, the interface definitions and all that kind of stuff. But then you just need good, communication. Communication is key. And I think we've had really, from the contractor team, the government team, the academic teams involved, Space Telescope, I think there's always been excellent communication, and that helps a lot. And in a lot of ways, it's also been very badgeless when it needed to be. And what that means is, we don't say you're from one institution, you're from another, but we get everybody in a room and we talk about things. In fact, we've been doing that with the commissioning. We were working, we literally meet every day, the entire team, and we go through the priorities for the next day, and we're communicating. The instrument, some being built by the European Space Agency or Canadian Space Agency are saying we need to do this. Telescope teams saying they need to do something. So it's a team effort.
So actually sort of following on from that, I wanted to ask everyone very briefly, what was like your one lesson learned from James Webb that you'd like to pass on to any future builders of great observatories? I've heard some of these already, but.
Here, so I've been on the program, as Lee indicated early on, for quite a long time. And I learned a lot of lessons. And so I could write novels and books and documentaries and all that on lessons learned. But probably my number one big takeaway is for a program as complex as JWST, you need a really rigorous test program. One that includes multiple methods of verifying performance. We had cross checks everywhere. One that includes pathfinders, so that you're not doing something for the first time on the flight hardware. You put something in front, learn your lessons on it, not on the flight. So having a really good, solid test program, I think, is probably my biggest lesson learned.
So for me, I did join the MIRI team before MIRI was built. So actually we were testing the verification model, and then we started with the flight model, etc. So I do agree, thorough testing is really key. Communication across all stakeholders. And for me personally, also, do not assume anything. If you have a question, just go to your colleagues and ask, or go to your partners and really double check, because sometimes things may not be clear enough, and it's really better, do not make any assumption, just double, triple check.
Yeah, I guess to answer yours and the previous question, I think from a systems engineering perspective, my takeaway is budgets are key, and not the financial kind. That's a different discussion. But understanding your roll up and understanding your uncertainty budget, in a lot of cases, the uncertainties is where we were really tracking, but understanding what an effect would have if I do go over this allocation, if I don't meet this goal, where are we going to take that from, where are we going to take that margin, and how much it affects the final performance. And in some cases it doesn't, and you don't have to worry about that, and you just keep tracking. So I would say that's my big systems lessons learned.
I guess I'll just do one, which you probably haven't heard, which is, I think, maybe the most important lesson learned as I've thought more about this, is actually, it's all about the people. And I think one of the reasons Webb was so successful is it attracted great people that were dedicated to it and stayed with it. And the reason was, it was exciting and ambitious, and like, why would you not want to work on this? That was kind of, so like that attracted all these people and they stayed with it. And that was, I think, one of the reasons we were successful.
I'll just add a couple of things. One is that I think you need a really close working relationship between system engineering and the science team from the very beginning. And I'll just throw one other one, which is that as you start to design these large flagships, you need people who do I&T involved from the very beginning. So you understand that as you come up with designs, you need to be able to figure out how you're going to test them before you launch them.
All right, another question in the room? Back in the back? She's behind you with the microphone.
Thank
We
you.
got one. Get here first, up here.
Me?
Yes, you.
Okay. First of all, congratulations, everyone. It's been so exciting to watch along in social media and all your press briefings and other appearances. Congratulations, and the future looks so bright for Webb and beyond. Given that you mentioned that some people have been on the program for 20 years now, and that we were expecting 20 years of scientific productivity out of Webb, could you each say a little bit about how you are identifying the leaders for that are going to be around in a generation to take over and transfer the knowledge that you've all gained over the last, the development timescale? Is there a process in place for finding your successors? And if so, are those processes different at the different institutions?
So essentially, when we're finished with the deployment and the wavefront alignment phase and then the science calibration, we hand over the keys to the Space Telescope Institute, and they have a whole flight ops team that has been training and shadowing each individual discipline for years and years now. Way pre-COVID for sure. And now that we're in the final stages of defining that transition, we'll have final reviews and make sure that what we told them, when we were training them is still the case and that we didn't learn anything, new features that we need to pass along. So we have some of those reviews set up in the next couple months, but we will be available, to phone a friend if they do run into anomalies that they can't solve on the ground there. But yeah, the Space Telescope Institute has done a really great job of identifying those people ahead of time. And they have really, they developed a lot of the flight ops products that we're actually commanding to the Space Telescope. So they understand the system very well. But yeah, it is a very crucial point to build in that mentorship in a program this long.
And I think if I can add, from the Northrop Grumman perspective, it tends to be more organic as opposed to prescribed. Prior to JWST, I actually worked on the Chandra X-ray Observatory. I was responsible for doing the alignment of the high resolution mirror assembly and then the telescope itself. And when I saw that people were starting to work on this really cool deployable telescope, I'm like, yeah, me. But I was young at that time. And, JWST and prior to that, Chandra, like Lee said, was attractive. And, I tend to be the old guy on the program at Northrop. We have a lot of young engineers who have come onto the program with that same level of excitement, and it's palpable. And so, it's just naturally organic that, people do tend to gravitate towards this program. And young engineers are just begging to continue on with the next big thing. So yeah, let's go build one.
Okay, over here. You have more? Okay, go ahead.
Yeah, so I just wanted to give the instrument team's perspective. So after commissioning, the instruments were built and designed either in United States, but not at the Space Telescope and Science Institute, Europe and Canada. And so the instrument design teams are in charge of commissioning, and they define the procedures, etc. But after commissioning, all those responsibilities of calibration and operations, they go to Space Telescope and Science Institute. So at the Institute, there are several teams, one per instrument, who have been working with the instruments really closely for many years and ramping up in all the knowledge and calibration techniques, etc., etc. And I have to say, for MIRI, I think in the last year, definitely during COVID, we have 2 new members, very young people, bright people who are really into, instrumentation, science, and really, they will take over at some point, and definitely we are ready for that.
And I'll just say from the project science side, we've been bringing in early and mid-career scientists to the project science team so they can take over, and also at the same time be involved in both the Roman telescope and then hopefully in the future on the next big flagship, bringing those lessons learned.
Okay, thank you. We have another question up here. Yes.
Question if you've used both sides of NIRCam, both Module A and Module B for wavefront sensing, and if you have, can you tell anything about the uniformity of the field given their proximity of the fields of view?
We have used both NIRCam A and B. We, for a couple different steps, the course phasing step with all of the pairs and to get it to align in piston, we did do some measurements on NIRCam B there. And then we also do what's called a course MIMF, or a single instrument multi-field measurement, where we look at many points across just the NIRCam field instead of the entire field of the other instruments. And we do a correction based on that. And we did that a few weeks ago. I'm losing track of time, but that correction really got us lined up nicely for what we're seeing now, and seeing that we have a great field of view, and like Lee pointed out in the images, that you can see off in the corners that things are really in focus. So yes, we've looked at B and it looks good.
So an interesting little fact, that image that everybody's been looking at, that's channel A and B, and we're making a mosaic. And that's why when people stretch that image, they see like the evidence of a mosaic in there. And so They're both working really well.
And Jim, you have a question from online?
Yeah, I have an online question. And this might be poaching on a later session or informing a later session. But looking ahead, how has Webb laid the groundwork for future technologies and capabilities into spacecraft designs for future great observatories?
I mean, I can probably help with that one. So, I mean, it definitely, I mean, I've used the analogy that, building Webb is a little bit like climbing Mount Everest. It's like after you climb it that first time, you set a path that other people can kind of follow. And I think we've done that in a lot of ways in terms of building a large segmented space telescope. Just take any example, like how to test the segments, how do we match the rays curvature? How do you test the telescope? We re-architected that several times, but we really set a roadmap to do all that. And this kind of gets back a little bit to the earlier question about, the mentoring and all. There was a lot of papers published on how we did that. So in addition to the people know-how, there's also sort of these, sort of document trail. And of course, we have all the engineering stuff that we've done. But I think it lays out, a good starting point. Now, the next ones are going to be different. They might be longer wavelength. They might require more stability. And so they're going to need some new improvements. But I think in a lot of ways, Webb, the really hard thing about Webb is this was the first, and I think now from here, it gets easier. And I think we're underestimating how much this is going to help the next one. That's one of my concerns, is that I think people think the next one's going to be so hard because it took 20 years to build Webb. But if we have learned our lessons, it should take a lot less time. And that's really, I think that's the challenge, is how do we do the next one in half the time? That's what I'm thinking about.
And I think that's a very appropriate end of the session. Jim?